Hello, everybody. Today I'm going to walk you through the beginnings of your lab on our extension of Extrema, finding maxes and mins. And you're going to do this today thinking about least squares regression. So, one of the most widely used fields in statistics and data science is finding a best fit model when looking at real-world data. It's very important to many people to kind of analyze situations and be able to predict how things are going to come out, whether you're manufacturing something, trying to figure out if you need more of this, need less of that kind of stuff right there. In many different professions, people are looking at data and trying to make some predictions about what the future will hold. One such way to do that, and for our case, a pretty straightforward mathematical way to do so, is with something called least squares regression. So I'm imagining at some point you have heard about the line of best fit. So think about a group of data. So you got all these data points, our independent X, our dependent Y. We have all those data points right there. And looking at this data, you're trying to find a trend, something that gives a good representation of this set of data. And we might have heard that called a line of best fit before. You're trying to have this line fit the data as best as we can. But what says that this line that I just kind of eyeballed and drew is good enough? Because you might have been thinking, kind of seeing that picture, well, what if something it's like that? Or maybe it's something like this. What really says that one of these lines, one of these prediction models is better than the other? In general, when we're finding models, they don't have to be lines. They can be logistic functions, they could be exponential functions, trig functions, they can be kind of anything. But for the simplicity of it, we're going to stick with lines for this first example, finding the line of best fit. And how we're going to do that is with a model obtained by this thing called the sum of squared errors. So thinking about our model, our prediction model, f of x, and looking at this sum s, what we are doing is we are taking the predicted outcomes at some x value, and we're seeing how it differs with subtraction from the actual measured outcome of that data point. And then we're going to square it, why it's called the squared errors. In general, the error is going to be the actual data value minus the predicted data value. Another name for this is a residual. You'll notice in our sum of squared errors formula up above, I reversed the order of that error, so we did the predicted value minus the actual value. It's going to make our calculations a little bit easier, and in general, we're allowed to switch the order because we're squaring it. Generally, subtraction doesn't like when you change the order, but because we're squaring this error, we're squaring the residuals, it doesn't matter which way we do it. And for our sake, it's going to just be a couple less negative signs we have to worry about. So that's why we're going to stick with this. We're going to stick with the predicted minus the actual to calculate our squared error sum. If we think about what our error looks like in a picture, you'll see down at the bottom of this page a little diagram here. We have 4 points, x1, y1, x2, y2, x3, y3, x4, y4, and we have our prediction model, this line, f of x. So we have our red data points, we have our blue model, which predicts outcomes for various x values. And you'll notice on this. In green, we have our residuals. We're going to call that D1, D2, D3, and D4. So what we are going to be calculating, or what I guess maybe a calculator I should say, is really calculating with this for this sum of squared errors, is we're taking the difference right here between the point and the model, D1, and we're squaring it. And we're adding D2 and squaring it, and D3 squaring it, and then D4 and squaring it, adding those all together. So for this picture, if I were to kind of estimate some values here, that might be something like, I don't know, 6 minus 4.8 squared plus maybe 5 minus 6.4 squared. Looking at D3, that would be 7 minus maybe 7.8, something like that, squared. Plus, looking at D4, that would be 10 minus, kind of looks like 9.1, maybe I'll just write 9.2 squared. And so our sum of square errors, if we're using my estimates, is about 4.65. What are we really trying to do when finding the line of best fit? We are trying to get this value to be as small as possible. In fact, up above here, if the model is perfect, then our sum of square errors is going to be 0. As a little aside, let's talk about why we're squaring things. If you had a handful of data points, your line of best fit, thinking about these errors if we're not squaring things, you will always be able to find a line where that error ends up being 0. Because with these positives, these negatives, you can always find a way to make that error sum be 0. So why we square things is because getting 0 is not easy for us to find maxes or mins. When we're trying to maximize or minimize something, if we can get 0, it's kind of a little weird. If we square these things, though, it takes all these values and makes them positive. And if we add them all together, we can now maybe a little bit easier way to think about it is getting this value that we can make as close to 0 as possible if they're all positive. We don't have to worry about things canceling. We don't have to worry about one point being really, really far away from the others. We're just trying to find the smallest value if they're all positive. So that is going to be what we're going to look at, why we're looking at the sum of the square errors so that we can minimize our value s and not have to worry about zeros and negatives and what that means in terms of trying to maximize and minimize. So we're going to be looking at this linear model that minimizes s. We have a name for it, least squares regression line, LSRL. I'm hoping that word regression seems familiar from past math classes. So our goal, if we're finding a regression line, is we're trying to find a function. We're trying to find a linear function. So aka we need its slope and its y-intercept that is going to minimize our residual squares summed together. Because if we can get that to be as small as possible, that means the error is as small as possible, so the data model will fit as close as possible. So what we're going to do, if we're finding a and b, we're really going to create a function s of a and b. That's going to represent our sum of square errors for our model, for our linear function ax plus b, for a given set of data. You'll see in a couple problems, or in a couple pages, we'll have a problem or two with, I think, 4 points, and then you'll do one with 5 points. Or maybe I got that backwards. Whatever. So our function s of ab, remember from the page before we were defining s to be the sum from 1 to n. We did the predicted outcome minus the actual outcome squared. And we're going to use our function, linear function, to represent this f of x sub I. So writing our function s with our linear model, that is going to be the sum from 1 to n of a times x sub I plus b minus y sub I squared. So please just note, oops, there's the highlighter. We're taking that function right there and we're trying to fit a best line. So we're going to use a linear function where a is our slope and b is our y-intercept. And we need to minimize this thing to find our line of best fit. So how do we minimize things? We're going to use derivatives. Oh, before we start taking derivatives, let's make a quick note here. Our points xi, yi, those are going to be treated as constants. So if we take that function, if we want to find the values of a and b that minimize the error, we just need to start with some derivatives. So let's take the partial derivative of s with respect to a. So if you recall from last year, or Calculus 2, when we have series like this, we can take the derivative and the integral of the stuff inside of a series. We could look at it as term by term, but in general, when we look at this, it's almost like ignoring the summation for a moment, and we can take derivatives and integrals as we normally would. So for this first partial with respect to a, we're going to have to think about this composition of functions, which is something squared. So we're going to take, don't forget our summation. I know we're kind of ignoring it for a moment, but we're not going to forget to write it. That power of 2, we can bring that down to the front. And then we need to take the derivative of the inside function with respect to a. There's where our a term is, and the derivative of that with respect to a would be x sub I. Doing a little bit of rewriting, that's the sum from 1 to n of 2x sub I times the quantity a x sub I plus b minus y sub I. And if you recall, when we were talking about series last year, we can break up this into a couple different series. It's going to help us actually do some math. So I'm actually going to write this as 3 series. I'm going to distribute that 2x sub I to all of these, and we can break up our sums at that plus and that minus. So we can write this as summation from 1 to n. Oh, and I forgot to mention one more thing. Our series, we're indexing that I. So anything that relies on that I value, changing from values 1 to n, we cannot factor out of the series. But anything that doesn't involve that I, that doesn't involve this change in what the series is asking for, we can just pull that out of the summation. So you'll notice when we multiply these first two things, this 2 and this a, they don't rely on I at all. So we can actually write that in front. So we have 2a times the sum from 1 to n of x sub I times x sub I, or x sub I squared. Our next multiplication, that's going to be 2x sub I times b. So we'll be able to pull the 2b out in front. And then we have the summation from 1 to n of x sub I is left. And then finally, when we do the 2x sub I times y sub I, looks like we'll be able to take the 2 out. And don't forget it's minus, so minus 2 summation, oh, that was bad, summation from 1 to n of the product of x sub I and y sub I. Now this might look a little challenging at the moment. Understand that we will be able to do some calculating with these sums right here. We just need to know what our data points are so we can actually calculate those values. So that is our partial derivative with respect to A. Now we got to do our partial derivative with respect to B. So our partial derivative with respect to B, so I probably need to have this kind of up there at the same time. I'm still looking at this function up here. So our derivative is going to start in the same way. We're going to have the sum from 1 to n of 2 times ax sub I plus b minus y sub I, and then we're going to multiply by the derivative of the inside with respect to b. b is just that term right there, so its derivative is 1. You could write times 1 behind that if you really want to, but we don't have to do that. We're going to break this up into 3 sums again. It's going to help us a little bit later. So we can think about this as 2a sum from 1 to n of x sub I plus 2b, and then we have the sum from 1 to n of 1, and we'll see if we remember how to find that sum really quick in a moment here, minus 2 sum from 1 to n of y sub I. If you recall, for this sum right here, this is just adding the number 1 n times. So we can actually rewrite this as 2a sum from 1 to n x sub I plus 2bn minus 2 sum from 1 to n of y sub I. So we're minimizing our function that is calculating the sum of square errors. We have the partial derivatives, so thinking to what we've done in class, we're going to find the critical points for this function. And how we do that? So we set our partial derivatives equal to 0. I guess I don't need to write that word our. We're going to set our partial derivatives s sub a and s sub b equal to 0. So what does that look like? Grabbing the stuff from the other page, we have 2a sum from 1 to n of x sub I squared plus 2b sum from 1 to n of x sub I minus 2 sum from 1 to n of the product xi and yi. And we're going to set that equal to 0. And we're also going to set our partial of b equal to 0. So that is going to be 2a sum from 1 to n of x sub I plus 2bn minus 2 sum from 1 to n y sub I is equal to 0. Now, how are we going to solve for our values a and b? Remember that a and b are our variables. Those are the things that we need to solve for. You might notice that it might be easiest to cancel this middle term right here. I'm thinking about this system. So what I'm actually going to do is I'm going to multiply this entire equation on top by n. And this bottom one, I'm going to multiply this entire equation by the summation from 1 to n of x sub I. Hopefully you can see that that is going to let us cancel those middle terms, but you do have to be a little careful when thinking about the other pieces, so write this along with me. In this first equation, we're going to have 2an summation from 1 to n x sub I squared plus 2bn summation from 1 to n x sub I minus 2n summation from 1 to n product xi yi still equals 0. And for the second one, we are going to get 2a. Please do not be tempted to make that the summation of xi squared, this is multiplying the two sums together. So the sum of x sub I times the sum of x sub I does not necessarily equal the sum of x sub I squared. So we're going to have, for the second equation, the sum from 1 to n of x sub I quantity squared. Those are different things. Minus, or plus, oh, you know what? I'm being silly. Why don't I make one of these negative? Let's make the bottom one negative so we can see that it cancels nicely. So I'll just throw a negative in front of that first thing that we did. And then let's make this minus 2bn sum from 1 to n of x sub I plus. That looks like that is going to be, and again, don't be tempted to just mix the x sub I and y sub i's together. This is going to be, excuse me, this is going to be 2 summation, sorry about that, x sub I from 1 to n, I forgot to write that, times the sum y sub I from 1 to n equals 0. All right, here we go. Now we're going to combine those two equations, and what do we get? I'm going to factor, actually I'm going to just divide a 2 out of everything. Hope everyone's okay with that. And for this first term, I'm going to factor out an a, and we are going to get n summation 1 to n of xi squared minus the square of the sum of xi's. The middle terms cancel. B's gone. That's going to allow us to solve for a. And we are left with minus n summation of the product of x's and y's plus the product of the sums. And that's going to equal 0. We've eliminated b, so we can solve for a. It's going to look so intimidating, but I promise in the actual calculation, it's not going to be so bad. Moving some things over and dividing, we're going to get that a is equal to n sum of the products minus the product of the sums, and then we're dividing by the stuff next to a, so we're going to divide that by n times the sum of the squares of x minus the sum of the x's squared. So please note again one last time, those things are different. Now that we have something that is going to, we have this thing that now defines how we can calculate an a value. If we have a set of data points, this is all stuff that's pretty easy to calculate, assuming you have smaller data sets. And even if you have larger data sets, computers are very good at calculating these things, aka a calculator could calculate these things very, very fast. We still need a way to define b, so we're actually just going to take this equation for a and plug it back into somewhere up top. And in fact, I'm going to pick that equation that we got from the second, or it's not second, but the first partial of s with respect to b. And I'm going to plug back in a right there. So we have our, and again, I think I'm going to divide the 2's away. So we have a sum of xi plus bn minus 2 sum of yi equals 0. I'm going to put my indices on my summations. And I'm going to solve for b, noting that we have that big, gigantic thing for a up here. So I'm just going to leave it as a so I don't have to write that thing again. But b is going to be equal to, we're going to move those two things to the other side, and then we're going to divide by n. So I'm going to do 1 times n out front, and that's going to leave us with, oh, folks, I'm so sorry. That 2 isn't supposed to be there. We divided the 2 away from everything. So we're going to get b equals 1 over n times the sum of the y's minus a times the sum of the x's. If you've taken a statistics course, this will look a little familiar here. Just a little note on the side here. If you take a sum of x values and divide by how many x values we had, this is just the average of the x's. And I'm going to use a little notation here that you see mostly in stats. We're going to call that x bar. That is the average of the x-coordinates. Similarly, 1 over n times the sum of the y-coordinates, that is going to be our average of the y-coordinates, which we're going to represent as y bar. So you'll note here that we can actually represent b as y bar minus a times x bar. Nice little way to represent that. So, as long as we have some data points, we can calculate all these sums. We can, oops, that's not good. We can get some values for a. And after we calculate a, if we find the average of the y's and average of the x's, it's pretty easy to find b. Thinking about whether or not this thing is, this critical point or critical points that we're going to find are going to be maxes or mins, let's think about the physical nature of this thing. Technically, these errors, you could have points that could be infinitely far away from our line of best fit. So our errors could technically grow without bound. There really can't be a maximum value for sum of errors or sum of square errors. However, we can minimize it. If we're doing square errors and we're thinking about these differences as positive values, the smallest possible error we could have is 0. We can minimize it. It can be smallest. So technically, if we find any critical values, it can be assumed that they're minimums, but we can actually show using the second derivative test that it is in fact going to be a minimum. So I'm going to do that for you here. Don't think you would always have to prove this for this type of question, though. So using the second partials test, remember we're going to need some second partial derivatives. So our second partial derivative of s with respect to a, so that is going all the way back to this first page right here, and we're taking the derivative of that with respect to a, noting we only have one term with an a in it. Our second partial with respect to a is going to be 2 times the sum from 1 to n of the x-coordinates squared. If you think about squaring x-coordinates, adding them all together, and multiplying by 2, I think it is pretty clear that that is going to be greater than 0. I guess technically it could be equal to 0, but assuming that all of our x values are not just 0, which they shouldn't be, so that would just be a repeated data point, it's going to be greater than 0. We'll also need for our second derivative test the second partial of b. So again, we're going all the way back up to where we took the first partial. Right here, we're looking at the derivative of that thing with respect to b. You'll notice we only have that term with the b in it, so we just get 2n. We need our mixed partial. So we're going to have to calculate that function d We're going to do that. I'm going to draw the Hessian matrix to help remind us how we do that in a moment. But going back up here, we're now taking the derivative of this first partial of A with respect to B. So now we're looking at this middle term right here. That is going to be 2 times the sum from 1 to n of the x-coordinates. So remember, to calculate that function d, we're going to do the second partials along that diagonal. We're going to do the mixed partials along this diagonal. And technically they should be different, but we're dealing with polynomial stuff. The second derivatives are going to be continuous. So we know that those are equal by Claros. So we're going to calculate, this is 2 sum, and I'm not going to write the indices because I'm writing small. The square of the x values, 2 the sum of the x values, 2 the sum of the x values, and then 2n. So we get our function 4n sum from 1 to n of the x-coordinate squared minus 4 the sum of the x values quantity squared. You might have noticed this hint that I wrote up here for you. This is not clear why. You need something called induction to prove this. If you make it into some linear algebra or proof-based courses, you will learn how to do proofs by induction. For right now, you're just going to use my hint. Using hint, can you see why this thing right here has to be greater than 0? N times the sum of the squares of x is going to be greater than the sum of x's squared. Notice we have a 4 in front of those, so because that thing in yellow is greater than that thing in blue, this difference has to be greater than 0. Therefore, if our second partial of a is going to be greater than 0 and our function d is going to be greater than 0, then a, b, that point is going to produce a minimum value of s. So there's our proof to show that this critical value that we're going to find is going to be a minimum. So from here, I'm going to do a full problem. We're going to take a look at the calculator to see the regression. We're going to look at Desmos to see a graph, and then I'm going to share with you what you are responsible for doing after. So find the least squares regression line for these points. We have 1, 2, 3, 4, 5 data points, so our n is going to be 5. This isn't any real-world data. This is just a random set of 5 points to just do some slightly easier math. So thinking about what we need to calculate. Remember, we're trying to find slope A, y-intercept B, and how we calculate those things. It looks like we need these sums. We need the sum of the products. We need the product of those sums. We need the sum of the x's squared, and then we need to square the sum of the x's. And then it looks like we'll also need the average of the sum of the x's, or the average x coordinate and the average y coordinate, and that a value to help us calculate our b. So we're using those things, so it might be helpful to have that written down in front of you. But I'm going to go through and I'm going to calculate some of these sums. The sum of the x coordinates, 0 plus 4 plus 5 plus 8 plus 10, that is going to be 27. The sum of the y coordinates is going to be 6 plus 3 plus 0 plus negative 4 plus negative 5. That happens to be 0. We need the sum of the x coordinates squared. So 0 plus 16 plus 25 plus 64 plus 100. which is 205. We need the sum of the product of the x's and y's. So that would be kind of looking at it 0 plus 12 plus 0 plus negative 32 plus negative 50, which is negative 70. And with all of these pieces, and noting that n is equal to 5, we can calculate our a value, which is n times the sum of the products, negative 70, minus, going back up here, it was the sum of the x's times the sum of the y's. Oops, went too far. Sum of the x's, 27, times the sum of the y's, 0, over, again, going back and checking here, we need n times the sum of the x's squared, and then we're going to subtract the square of the sum of the x's. So we're going to do 5 times the sum of x squareds, which is 205, minus the square of the sum of the x's, which is 27. Please use a calculator. Don't try to do that by hand unless you really, really want to. I got negative 175 over 148. And now that we have our a, calculating our b, we need the average of the y-coordinates. So that is going to be 0 divided by 5, because we take the sum and divide it by how many data points we have, minus the a value, negative 175 over 148, times the average of our x-coordinates. So that is going to be 27 over 5. And again, calculator is going to be handy here. I got 945 over 148. So our least squares regression line, our model, our line of best fit, is going to be y equals negative 175 over 145x plus 945 over 148. In case you do not recall doing this on a calculator, I'm going to show you how we can get this on our TI-84s. Let's see. I need to do... Sorry about this. I thought I had it up. There it is, TI-80. TI Smart View for me, so I can show you how that works. Did this not bring that up? There it is. Okay, it's going. Sorry about this. I thought I had it up. So, to make or to find our lines of best fit, we're going to go to Stat, and we're going to edit our lists. If you have anything in list 1 and list 2, if you go up to L1 and press clear and go down, that will get rid of everything. And if you have stuff in list 2, so say I had, come on, move over. If I had like 1 and 2 and I wanted to get rid of all that stuff, if I just go up to L2 and I press clear and move down, it gets rid of all of it. So we're going to go use our data points. So our x values are 0, 4, 5, 8, and 10. And our y values are 6, 3, 0, negative 4, and negative 5. To find our linear regression, if you remember, we're going to click on Stat again, and we're going to go to Calculate. There's actually 2 places where you could find the linear regression model. I like using 4 for the slope first. They'll both give you the same thing. But if you go down to 4 for LinReg, linear regression, hit enter. Please verify that the lists that you entered the data points in are the ones listed here. So I plugged mine into L1 and L2. If you did like L3 and L4 for some reason, please just make sure to check or change those, and recall that to type the list names, it's second and then the numbers 1, 2, 3, 4, 5, or 6. Those are your L1, L2, L3, L4, L5, and L6. But as written, I'm happy with those. I don't need the frequency list. That we're not going to store this because we're not going to look at the graph on our calculator. We're just going to go calculate. So, looks like I get a regression model y equals negative 1.1824, so on and so forth, x plus 6.38513. So that's what the calculator says our line of best fit is. Now, if I had a second calculator in front of me, I could leave the screen up and ask you to calculate the decimals for those fractions that we had. So if you do negative 175 divided by 148, would you look at that? That is the slope that the calculator found for our linear regression model. And if we do 945 divided by 148, there's that 6.385 number that was the y-intercept. So this is a way that your calculator actually calculates this line of best fit. It does those summations that we did. It's got a pattern, and it knows the pattern, and it can calculate that for us really, really fast. But now we know how the calculator is doing this, which I think is pretty cool. Now, the next thing that I would like to do is look at Desmos. And show you how to get this to show up on Desmos. So sorry, this is cutting it off a little bit on the left-hand side. I apologize. I know that you're not seeing this. So to make a table, if you go over to the left, so where my mouse is, I'm sorry, again, it's cutting off, and I'm going to the left, and there's a little plus sign, and if you hover over it and it says Add Item, if you click on that, you can add a table. So please add a table, and we're going to go through, and we're going to add in our table of values again, like we did on our calculator. A little bit easier this time. 6, 3, 0, -4, and -5. Now, you will see on here our data points. I guess I have to zoom out a little bit. You can see our 5 data points right there. To have Desmos give you its regression model, what you're going to do is we need to use y1 and x1. So you do have to type in the subscripts. So if you type in y, which you can't see, I just typed it in, I'm sorry, it's cutting it off right here. To make a subscript, if you hold shift and hit the key next to 0, that's going to allow you to make a subscript. So you're going to have y1, and instead of equals, you're going to use a tilde. Tilde is shift and then the key to the left of 1. And then if you type in, if you type in A and then X, and then we need to do our subscript 1 again. So remember, that is shift, the key to the right of 0, then 1, and then you got to move to the right, and then we can do plus B. You will see our line of best fit. You'll see our A value right here is the one that the calculator gave us. You'll see that the B value is the one that the calculator gave us. There is our line of best fit. And we can see that all of these points are relatively close to this line. This is the line that is closest to all of those points as possible. So remember, you need to use the subscripts, you need to add a table, you need to use the tilde instead of an equal sign, and then Desmos will actually give you the regression stuff for you. You'll notice right here, again, it's cutting off, but this number right here is our r, and r, or this is r squared up here, and this is r. Remember, the closest that r squared is to 1, the better fit this is. So this does about a 96% good job in fitting to our data points right here. Okay, so to wrap up here, what are you going to do for me? You're going to do this with a quadratic regression model. I know that sounds a little bit intimidating, but you're not going to have to solve for A in this way. I'm going to give you a different way to do that. So you're going to use our sum of squared errors formula right here. We're going to flip it back to have the actual value minus the predicted value. So you're going to do y minus a x sub I squared minus b x sub I minus c, and you're all going to square that. Notice that our function is now in terms of 3 variables, a, b, and c. So when you're doing this, what are you going to have to calculate? You're going to have to come up with 3 partial derivatives this time. You can do that in this workspace here. Then what you're going to do is you're going to set those things equal to 0, and you're going to set up a system. So you're going to find the things that are being multiplied to A, B, and C's in these. And for almost all of these, you're going to have a summation sign, okay? It's going to give you a similar feeling to this stuff. You're just going to rearrange it so that instead of 0 over here, you're going to move the thing without the A, B, or C to the other side. Finally, once you have this system set up fitting this model right here, I'm going to actually have you do some calculations of those values, and then you can use matrices to actually calculate our values for A, B, and C. If you don't remember how to do that, I will show you at the end of this video here. If you do remember how to do that, you can get going on your partial derivatives, setting up your system to solve for A and B, finding the value of these sums for this data set right here. It's only got 4 points this time, and then you can plug in those numbers right here to solve for your values of A, B, and C. Please, I want you to use Desmos again to make your table and show the quadratic regression model like I did for the linear one. You'll need to print that out. So make sure that you print out a picture of that and attach that to your lab before you turn that in. So I will definitely be needing to see your work, this system right here, your solution, your regression equation, and then you're going to attach a picture that's going to look similar to this. Please note that this is not the picture that you're getting. This is for a different set of points. So with that, if you remember, I think it was in Algebra 2, that you learned how to solve systems using matrices. If you know how to do that, you can get to work. If you don't, I'm going to run through on the calculator how to do this. So let's say that in your system, you calculated your sums of the different things, whether they were like x's or x squareds or x times y's, whatever they are, and you got values 2, 3, 4, 5, 2, negative 1, 5, negative 2, and 3. Anything that is going to go in front of that A, B, and C, those are going to be our coefficients. We're going to put those into one matrix. We're going to call that matrix A. The values that are going to be on the other side that we're going to calculate are constants over there. We're going to put that into another matrix. This, I guess I should say this is a 3 by 3 matrix. This is a 3 by 1 matrix, 3 rows by 1 column. And how we can solve a matrix equation, because we cannot divide matrices, we multiply by the inverse. The other thing you have to know about matrix multiplication, it is not commutative. So when we multiply the inverse of A, we're going to have to do that on the left because we can't do it on the right because we can't squeeze it in between the x and the A. This is going to cancel each other, but because we multiplied A inverse on the left, we have to multiply A inverse on the left on the other side as well. So this x is really this matrix that solves for our variables. It's really this x, y, z. We calculate that matrix by doing A inverse times B in that order. You cannot do B times A inverse. It will not work. So how do you type all this stuff into your calculator? We're going to use this example right here, and I will show you how to type that in on a TI-84. So to make matrices, you'll see over here on the left in blue, there's a word matrix. So you're going to hit second, matrix. To create a matrix, you're going to go over to the edit menu. We're going to just pick A for the first one. So you're going to hit enter. We need to make a 3 by 3 matrix. So 3, enter, 3, enter. That's going to give you this. Now we're going to type in our values. And you can use enter for it to move, or you can use the arrow keys. So 2, enter, 3, enter, 4, enter, 5, enter, 2, enter. Negative 1. Sorry, because I'm on the computer, I have to make sure the negative is doing that, not the minus sign. 5, negative 2, enter, and 3. There's our matrix A. Now we just need to escape. So if you do second mode to quit, or we're going to go back and make a second matrix. So you can just hit second matrix again. You'll note now we have matrix A, it's 3 by 3. We don't want to overwrite this, so when you go over to edit, please make sure you scroll down so that it's highlighting B, and then you can click enter. We need to make a 3 by 1 matrix, and we're going to type in the numbers again from the notes. That was 1, 12, that didn't work, 12, no, come on, 12, and 7. Now we need to go back to our home screen, so I'm going to hit second mode to quit back to our home screen. Now, to multiply matrices, you're going to go back to the matrix menu. Now we're not going to go to edit, we're just going to stay on the names thing, and we're going to click enter to bring up A. To make it an inverse, you can either click this button right here. It's under matrix, that's why it's attached to the matrix one, because we use that for matrices all the time. Or you can actually put a power of -1, that will work too. But I'm going to delete that and show you that pressing this button will just give you that inverse notation. And then we need to multiply that by matrix B. You don't even have to type that multiplication symbol if you don't want. We need to go back to our matrix menu. We're going to make sure we click on B, not A. So you should see A inverse times B. We hit enter, and we get this. Gross, nasty, but if these happen to be able to be fractions, the calculator can do that for you like it can do with any decimal. If you go to math and you go on fraction and you hit enter twice, you can see there would be our X, Y, and Z value that solve that system in the notes. Not very pretty, and doing that by hand would be a pain in the butt because row reduction of matrices can take quite a while. If you have any questions, please make sure to ask. If anything isn't clear on what you're supposed to do or you're stuck on something, ask me, ask around. This is going to be due next week, so don't put it off too long. And yeah, hope you have a little bit of fun with this.